Have you ever watched a road roller at work and suddenly started feeling the vibration through your entire body? The ground shakes, nearby equipment responds, and a simple question comes to mind. How can a single machine make everything around it vibrate with such force? What exactly creates that vibration? Where does it come from? And how is it transferred deep into the ground? In this video, we'll break down that engineering puzzle step by step. At first glance, a compactor roller seems deceptively simple. It moves back and forth over the ground, making it denser. But in reality, it performs one of the most critical tasks on any construction site. It creates the foundation that everything else depends on. In its natural state, soil is full of voids. Air is trapped between particles of earth, sand, and aggregate. If those voids are not eliminated, the ground will gradually settle over time. That settling leads to cracked asphalt, deformed road surfaces, damaged foundations, and costly repairs long after construction is complete. A compactor roller prevents these problems before they become visible. It transforms loose, unstable material into a dense and predictable base capable of supporting heavy loads for decades. For a long time, it was believed that compaction depended mainly on weight. The heavier the roller, the better the result. And weight does matter, but only at the surface. Static pressure effectively compacts the top layer, while deeper layers remain largely untouched. Everything may look perfect from above, but beneath the surface, a weak zone still exists, waiting to cause future failures. That's why roads can deteriorate even when heavy equipment is used. The problem isn't mass, it's penetration depth. To fully change the structure of the soil, you need more than pressure. You need energy that can travel downward. The solution is controlled vibration. When vibration is added to the machine's weight, a completely different process begins. Vibrational waves propagate through the soil, causing particles to shift, lift, and rearrange into a tighter configuration. Air is expelled, the structure becomes uniform, and the load-bearing capacity increases dramatically. This vibration is not random. It is precisely controlled in terms of frequency and amplitude, depending on soil type and layer thickness. The combination of mass and properly tuned vibration is what makes modern compaction truly effective. The source of this energy is hidden inside the steel drum. At its center is an eccentric shaft fitted with unbalanced masses, intentionally offset from the axis of rotation. When a hydraulic motor spins this shaft, centrifugal forces are generated and transmitted to the drum at a very high frequency. As a result, the drum produces thousands of controlled vibrations per minute, delivering energy directly into the ground. By adjusting vibration parameters, the operator adapts the machine to specific site conditions. This turns the roller from a simple heavy cylinder into a precise engineering tool. To ensure this system operates smoothly and reliably, modern rollers use a hydrostatic transmission. There is no conventional gearbox, no mechanical gears, and no abrupt shifts. A diesel engine drives a dual-circuit hydraulic system with variable displacement pumps. One circuit controls machine travel, while the other powers the drum's vibration system. Speed and direction are regulated by controlling both the flow rate and direction of the hydraulic oil. This design delivers smooth motion, precise control, and high traction even in difficult conditions. The machine moves predictably and without jolts, a critical factor for achieving consistent, high-quality compaction. One of the most unusual features of a compactor roller is the absence of a throttle pedal. This is not a simplification, it's a deliberate engineering decision. Compaction quality depends directly on maintaining a constant travel speed. Any acceleration or deceleration leads to uneven energy transfer into the ground. That's why speed control is integrated directly into the travel lever. The operator sets the desired pace, and the machine automatically maintains it, regardless of soil resistance or slope. This reduces operator workload, minimizes errors, and ensures consistent results on every pass. Unlike cars and trucks, a compactor roller does not steer by turning its wheels. Instead, maneuverability is achieved through a central articulation joint, allowing the machine to bend in the middle. This design choice is critical. During operation, the drum must remain parallel to the surface and maintain full contact with the ground at all times. If steering were done by wheel angle, part of the drum would lose pressure in turns, resulting in uneven compaction. The articulated frame solves this problem. The front and rear sections of the machine move relative to each other, while the drum continues to apply uniform pressure across its entire width, even on curved paths. Operating a roller is not only a mechanical challenge, but also a physical one for the operator. Continuous exposure to vibration over long periods can have serious health consequences. The spine and joints are affected first. Over time, fatigue accumulates, concentration decreases, and the risk of operational errors increases. Without proper protection, an operator can lose effectiveness quickly, even if the machine itself is in excellent condition. That's why modern rollers place strong emphasis on vibration isolation. Rubber dampers and vibration isolators are installed between the vibrating drum and the rest of the machine, absorbing a significant portion of the oscillations. Additional drum suspension systems are used, and the cab and seat are designed as an isolated zone. As a result, vibration remains where it is needed, in the ground, not in the operator's body. This allows the drum to operate in aggressive compaction modes without compromising comfort or long-term health. But how do you stop a machine that can weigh 5 to 10 tons, especially when working on slopes or ramps? A compactor roller has enormous mass and inertia, so safety is built around redundancy. For this reason, two fully independent braking systems are used. In normal operation, service braking is achieved through the hydrostatic transmission. When the operator returns the travel lever to neutral or reduces travel input, oil flow in the closed hydraulic circuit drops to zero. The hydraulic motors then smoothly decelerate the machine. This is the primary braking method in everyday operation. On some models, the system is supplemented with hydraulic disc brakes mounted on the drive units. These provide an additional layer of safety and are used in specific operating conditions. The parking brake is a spring-applied, fail-safe mechanism. By default, it remains engaged and holds the machine stationary. It is released only when hydraulic pressure is present. As a result, even in the event of a total hydraulic failure or engine shutdown, the roller remains securely immobilized and cannot move unintentionally. During operation, a compactor roller generates a tremendous amount of heat. The diesel engine runs under constant load. Hydraulic oil circulates continuously at high pressure, and braking components heat up during every deceleration. If this heat is not properly managed, the consequences are severe. Hydraulic oil degrades, seals break down, and the service life of critical components is drastically reduced. That's why the cooling system plays a critical role. Radiators and heat exchangers with forced airflow maintain proper operating temperatures for both the engine and the hydraulic system, protecting the oil, seals, and the machine as a whole. In addition to the main cooling system, the vibratory drum itself also contributes to heat dissipation. Heat generated inside the vibration mechanism is transferred through the drum shell. Thanks to its large mass and surface area, the drum effectively releases this heat into the surrounding environment, functioning as a passive heat exchanger. Despite their similar appearance, there is no such thing as a universal compactor roller. Each type is designed for a specific task. Smooth drum rollers are used for asphalt compaction and finishing layers. Pad foot rollers are designed for cohesive soils and deep layer compaction. Pneumatic tire rollers apply uniform pressure through multiple rubber tires and are often used for final surface finishing. Combination rollers integrate different solutions and are suited for multi-stage work on a single job site. Choosing the wrong type of roller leads not only to poor compaction quality, but also to unnecessary stress on both the operator and the machine. Modern rollers are highly specialized and expensive pieces of equipment, and their cost depends heavily on type, size, and configuration. Entry-level models typically range from around 50,000 euros to 120,000 euros. Medium-sized road rollers with vibratory systems usually fall between 120,000 euros and 250,000 euros, while heavy-duty soil and combination rollers can cost 250,000 euros to 500,000 euros or more, depending on the manufacturer and level of equipment. High-end models equipped with compaction control systems, climate-controlled cabs, and telematics can exceed these ranges significantly. A modern compactor roller is more than just a heavy machine. It represents a balance between compaction efficiency, structural durability, and human health. A good roller compacts the ground to the required depth, operates reliably for years, and protects the person who controls it every day. And if you'd like to learn how other types of heavy machinery work, let us know in the comments.